For inviting me, and it sounds like a very interesting speaker series with interdisciplinary interest and groups. I'm really looking forward to getting some reactions. So this is actually a work in progress. So we have the first version of the paper up on the archive, but we are actively revising. So your any comments and feedback would be most welcome. I just wanted to acknowledge my collaborators. It's a part of the larger project I've been engaged with for the last several years, and so Eli Ben Michael was my former postdoc. He's now assistant professor at Carnegie Mellon in statistics and public policy, and then Jim Greiner is a professor in Harvard Law School, who actually put together this amazing RCT that I'm going to talk about today in the field of criminal justice. He and I've been a longtime friend. Meredith Huang is a current postdoc at Harvard, working with me, who'll be assistant professor at Yale. And Jichou Jian is my former postdoc, who's back in China, Sun Yat University, and he's a professor there. And Soren Shin is a graduate student at Harvard in the government department. So it's a good group of interdisciplinary expertise. Okay, so this paper is looking at this AI-human interaction. So I just wanted to sort of motivate the talk by talking about, briefly mentioning this massive technological changes in the recent years. We've been ourselves interacting with data-driven algorithms everywhere in our daily lives, where whether the stakes are high or low, we are constantly interacting with these algorithms. And as we all know, some of the generative algorithms that's out there now may soon or may have already replaced simple human tasks. With this background, today I want to focus on the fact that humans still make many consequential decisions. And in fact, actually, humans still make many inconsequential decisions as well. So for example, when you're doing online shopping, at least I haven't reached a point where I'll just say, hey, Alexa, do the grocery shopping for me. I still make a purchasing decisions myself, even though the recommendations are given by the algorithms. So I think we see a lot of things we see is that humans are still making the final decisions, and with the help of AI or algorithm recommendations. Okay, so in particular, the focus of this talk is looking at consequential high-stakes decisions, which we haven't really outsourced to the AI or algorithms yet. Okay, this is true even when human decisions can be suboptimal. In fact, we've seen, algorithms can beat humans in many areas. So I wouldn't be surprised in the future that in terms of accuracy and other measures, the algorithm may actually surpass the human, decision makers' capability. But maybe we still want the humans to be in charge. Maybe that's because we want to hold somebody rather than something accountable. So I think there's a lot of debate about how much of our decisions should be or can be outsourced to the AI or algorithms. Okay. So with this background, I would say the most prevalent system is what you can think of it as AI-assisted or algorithm-assisted human decision-making. So humans make the final decisions with the help of AI recommendations. As I said, like this includes routine decisions made by individuals. Online shopping would be a good example of that, but also includes the consequential decisions made by doctors, judges. It's everywhere. In the criminal justice system, there are every basically stage of criminal justice system, whether it's a cash bail decision, that's what I'm going to talk about today, or sentence decisions, there are AI recommendations. And if you go to the hospitals, the doctors actively relying on some of these algorithmic recommendations as well. So you see this You see this, everywhere even when the stakes are high. So some of the questions that I'm interested in, not just this project, but many other projects I'm currently working on. How do AI recommendations influence human decisions? So for example, does AI help humans make more accurate decisions? Does AI help humans improve the fairness of the decisions? Okay, so it's my interest is really about how these machines, algorithms affect the way that we make decisions. Okay, I've been interested in this question for some time, but when I started studying this, many people have focused on the accuracy and fairness of AI recommendations themselves. To some extent, like this is an easier one to study. In the end, algorithm and AI are mathematical object. We can actually study their properties pretty well. Humans, on the other hand, is much more complex. It's much easier to fix the bias of algorithm than the bias of the humans, as we all know. And as a social scientist, we all know the complexity of the humans and why they make a certain decision. It's often difficult to know. There's also the heterogeneity across humans. Every human is different. They think different ways. So it's a lot more complicated object. Perhaps for this reason, relatively few people have researched their impacts on human decision. They really focused on the accuracy and fairness of the AI recommendations. I think what's interesting is that interaction between the bias of AI or algorithm with the human bias. How do they interact? Because if you think about the human making the final decision, even with the same exact algorithms, different humans will make a different decisions because they react differently to the same recommendations. So I think this is to say just there's a lot to be studied with the human computer algorithm interactions. Okay. But today I want to focus on introducing a new methodological framework for experimental evaluation of sort of addressing some of these questions. In particular, I'm going to look at the experimental design where you randomize two decision systems. One is decision-making systems. One is just let the humans decide, and the other one is the humans make a decision with AI recommendation. So you're going to randomize which decision-making system you're going to use across different cases. And I'm going to introduce you the methodology to analyze the data from this experiment. And the idea is to compare the performance of human alone decision with human plus AI decision. And in addition, we're going to also try to compare with AI alone decision. Like what would happen if you outsource the entire decision to the AI, or humans blindly follow the AI recommendation. So what's interesting is that even though the experiment does not include the arm that lets the AI decide everything, we can actually evaluate the accuracy and other properties of these different decision making, three different decision making systems. Okay, I'm going to discuss this in the context of pretty unique field experiment where we're going to try to evaluate pre-trial public safety assessment. So this is the algorithmic recommendation that judge receives in the U.S. criminal justice system when they're making a pre-trial decision, usually a cash bail decision that I'm going to discuss more in detail. Okay, so before I get started, discuss my own context experiment, I'll just briefly go over this controversy over the COMPAS score, which probably many of you already know. There's a well-known article by a group of journalists at the ProPublica. So basically, they found that risk assessment score, that COMPAS score, that's used in the criminal justice system in the U.S. appears to be biased against Black defendants. So here, you have two people who were arrested for the sort of same type of crime, petty theft. And the white man was rated by the algorithm as low risk, whereas the black woman was rated as high risk. Okay? Similarly, there's another example of two individuals who were arrested for drug possession. Again, the similar type of crime. The white male was rated as low risk by the algorithm, whereas the black male was rated as highest risk by the algorithm. So the journalists looked at the distribution of this risk score and then found that the white defendant risk score, which is on your left, has a lot fewer high risk cases than the black defendant's risk score, which is on your right. So this sort of prompted, okay, the algorithm may have racial bias, and that could be a problem. And of course, as I emphasized just a couple slides ago, what matters is not really the algorithm's bias, but it's actually how that influences the judge's decision. Because at the end of the day, human judge makes a decision. So the bias of the algorithm, what matters is how that interact with the bias of the human. Because human could be, we all know that the human is also biased, right? So that's what I think. Just looking at the bias of the algorithm itself is not necessary. Doesn't tell you the entire picture. Okay, so given this sort of well-known study, what we're going to do is to look at the particular algorithmic recommendation called the pretrial public safety assessment. I'm going to call this PSA. Okay, it's not the same as the COMPASS score, that well-known COMPASS score, but it's sort of the same idea essentially. It's AI recommendations often used in the U.S. criminal justice system, different jurisdictions. And they're used at the first appearance hearing. So this is the hearing where if you're arrested for certain crime, then you appear at this hearing, and then judge will primarily make the two decisions. So first, the judge will have to decide whether to release arrestee pending disposition of criminal charges. That is, you were just arrested for the crime, but you haven't been you haven't been found guilty. So you may be actually completely innocent. But the judge has to decide before the formal proceeding whether arrestee should be released. Okay. If released, under what conditions? So they may impose some cash bail or the monitoring conditions. Okay, so those are two decisions the judge is going to make. The goal here is from the perspective of a judge, the goal is to avoid the predispositional incarceration while preserving public safety. So again, as I said, these people can be innocent. So you want to avoid the unnecessary incarceration, but at the same time, you want to preserve public safety. So you don't want to release everybody. Okay, so you have to make a decision of who should be released. By law, judges are required to consider 3 risk factors along with other factors. The 3 risk factors are: arrestee may fail to appear in court. So for the formal proceedings, they may not come back. I'm going to call this FTA, fail to appear. And arrestee may engage in new criminal activities. So that's, I'm going to call this NCA, right? So this is the case where arrestee gets released and then they commit a new crime. In particular, they may also engage in the new violent criminal activity. So I'm going to call this NVCA. That's also a concern. Okay. So what is PSA, Public Safety Assessment? It's an AI recommendation to judges. It classifies arrestees according to these 3 risks. So it assigns a numeric score for these 3 risks. Okay. It's derived from an application of a machine learning algorithm to a training data set based on past observations. So training data set come from the sort of entire country. It's a sort of 500,000-600,000 arrest record, and they use some machine learning algorithm to do the training. Again, it's different from the compass score, but it's the same idea. Essentially, trying to help the judge make this decision of who should be arrested, who should be released, and who should be kept in jail. All right, so we've done this to evaluate this PSA. We've conducted a field experiment. So this is a real-world experiment. Was done in Wisconsin, Dane County. So Dane County is where the Madison is. It's the home of University of Wisconsin-Madison, not too far from where you guys are. The PSA is weighted indices of 10 factors in this jurisdiction. Age is the only single democratic factor. They don't use gender or race to avoid the direct discrimination. And then the rest of the factors are drawn from criminal history. Okay, so prior convictions and FDA. So you can think of this algorithmic recommendation is like really mostly based on the prior convictions record. Okay. So let me first tell you what it is, and then I'll show you the details. Okay. So the PSA scores there's basically 3 scores. There are 2 separate ordinal 6-point risk scores for FDA and NCA. So for each of these, there's like a 6-point score. And then for NVCA, there's like one binary score for the new criminal activity. Okay. And finally, we have aggregate recommendations. So combining these 3 numbers into basically overall recommendation, and that consists of signature bond. So this is a specific term for just unconditional release, basically. So you can basically sign a piece of paper and then get released, and also a small and large cash bail. Those sort of is the recommendation category. Okay. Let me show you the actual algorithm look like. So it's actually very simple, and this information is publicly available. So a lot of times when you use this kind of recommendation system in the public policy, they make it all available publicly because of the reason of the transparency. And also it's relatively simple, so that people can understand how different factors map into the final recommendation. So a lot of times in public policy and even medicine, I think we see the recommendation rules being relatively simple and transparent, publicly available. So this is one such a example here. So here you see the risk factors, and basically what happens is that based on your prior criminal history and the age, you get some points. Okay. And then you are going to add these points for each category. And then once you add the points, then there's sort of the mapping from your point, sum of the points to 6-point scores for FDA and NCA, and then the binary score for the NVCA. So it's very, very simple. I think it's like something similar to the Canadian naturalization steps where you get a points and then you have a little table and whether you get a passport or not. Yeah, so it's the same idea. And then once these scores are calculated, there is overall recommendation. So it turns out that if you get NVCA equal 1, then you automatically cash bail is your recommendation. But if the NVCA is equal to 0, then the final recommendation depends on FDA and NCA score. And if you round in this like a darker orange, you get a cash bail recommendation. Whereas if you get this lighter color, then you get the signature bond that is being released on your recognizance is the recommendation you get. The white parts are the ones that are like it's impossible for these values to be realized based on this scoring system. Okay, so that's basically the algorithmic recommendation. So It's relatively simple. So the machine learning part comes in determining these integer weights. Machine learning part comes in this like aggregation, how you aggregate it, and then how you sort of assign these different weighting information. Okay, so that's how it looks like. Now it's important to note that the judge may have other information about an arrestee that I don't have as an analyst. So, for example, they may have affidavit by a police officer about the circumstance of arrest, or there may be a defense attorney in presence. Many arrestees don't have that in this jurisdiction. I'm analyzing really a petty crime. It's not a high profile murder or anything like that. So a lot of cases they don't have a defense attorney necessarily, but they may inform about the arrestees' connections to the community. Like they may have a family or kids, or they may be employed. So if you're incarcerated, that may cause a problem. So that also affects the judge's decision that we don't really observe. So the field experiment was done the following way. So actual randomization was difficult for the logistical reasons. So we ended up doing semi-random, quasi-random assignment, where the clerk assigns the case numbers sequentially as the cases enter the system. So someone gets arrested and they get assigned the ID number. And then PSA is calculated for every case, okay, using the computer system. So that what's important here is that we know AI recommendation for every case. And if the first digit of the case number is even, the PSA is given to the judge, okay? And if it's odd, then PSA is not given to the judge. And because the way that the people who appear is not necessarily the same as the people who get arrested, order in which they get arrested, it's essentially random. We check the covariate balance, and it looks all what you would expect.
Is it the first digit or the last digit?
Last digit.
Okay, that makes more sense.
Yeah. Sorry about that. That's a typo. Last digit.
Just there's another clarifying question in the chat from Douglas. Douglas, I'll just read it out. So if the arrest rates reflect the reality of over-policing of certain communities, don't these just get passed along by the algorithm to the judge? That is the probability.
What was the first part? Arrest. I couldn't hear.
Beg your pardon. So if the arrest rates reflect the reality of over-policing of certain communities, don't these just get passed along to the algorithm by the algorithm to the judge? The probability of rearrest is not equal to the probability of reoffending, is it?
Yeah. So the probability of rearrest is definitely not the same as probability of reoffending, because arrest doesn't mean that you actually committed a crime. There might be over-policing. A lot of people may be innocent. So the cases that come in may not necessarily actually the people who actually committed a crime. That decision happens later. So we're looking at the pre-trial period. So before the trial actually happens, what's going to be the behavior? Yeah. So those are good questions. So the data I'm going to show you is actually first half of the data that we have. It's not a full data set, but so it's about 2 year worth of the data set. We do have a full data set, but we'll be using that to write a more substantive paper. But we have made this preliminary data available, publicly available. So if you go onto my website and look at the replication data, then you see this data set is publicly available. So you can analyze and you can do fun things with it if you like. Okay. All right. So here is the report the judge actually gets to give you a better sense of what's happening. So here is the 3 scores. So the new violent criminal activity is the binary score, and then there's 2 6-point scale score. Okay. And there's a charge here, and here is the factors, risk factors, and their values. So in fact, the judge does receive the risk factors, whether you're in the treatment group or control group. So what's really adding, the information that's being added is how they weight, how the algorithm weight different factors, and then how they aggregate it into these like 3 scores, and then the final recommendation, which in this case, it's a release recommendation, which says signature bond, which means that this person, AI is basically saying, release this person. Okay, so it's really like, what is algorithm adding? It's just how these different pieces of information should be aggregated into the decision. Okay, so there's no like a new information. In fact, the judge has more information than the algorithm. The algorithm has only a very small subset of the information. You can also see the recommendation, like there's a condition, release condition, but in this paper, we're not going to analyze this part. Okay. All right, so let's look at the data to just give you a sense of what the data look like. So there's 2 groups, PSA provision and no PSA provision. There's 3 decisions that I classified. One is a signature bond, and then the cash bail I classified into small and large. Now the small is like less than $1,000, so it's again, it's a petty crime, so it's not a $450 million bond or anything like that. You see that there's more male arrestees than compared to the female, about 20% female, but sort of relatively equally balanced non-white and white male arrestees. If you think about Wisconsin-Madison, which is very white, I think it's more than 90% white, this shows that the non-white arrestees are overrepresented in the arrest population. In the female, there's fewer number, but a white female is a greater number than the non-white female. If you look at the re-arrest, you can see that about 30% of the people either fail to appear or commit new criminal activity, or arrested, accused for committing a new criminal activity. NVCA is relatively rare, so only 6% of the cases come back with the committing the violent criminal activity. In terms of decision, you see that the majority of decision, about 37% each, so more than 70% is actually signature bond. So the judge releases more than 70% of the people without any condition, without any cash bail. Whereas the cash bail is about 25% or so with the varying amounts. But we're going to analyze the cash bail or not. We're not going to analyze the amount in this case. Some people are detained because they're unable to pay, and others are released because they're able to pay the cash bail. Okay, so the first thing you can do is to do difference in means, right? Like it's okay. Once you do experiment, like exciting part is when it's compare the treatment group and control group. And so here it's a little bit complicated graph, but you see the overall female, male, and then for male, which we have relatively large number of observations, I'm going to split it into non-white and white. Okay, and if you remember, there's 3 decisions: signature bond, small cash bond, large cash bond. And so we can look at the impact of providing this PSA recommendation on judge's decision, and the y-axis represents the probability. Okay, so as you can see, like overall, it's effect is on average 0 essentially. It's relatively precisely estimated because you can see like it's like about negative 4%, 4 percentage point to the about 4 percentage point, right? So even if there is some effect on average, it's relatively small. And you can also see the same kind of pattern across different subgroups, although the confidence interval is a little bit wider. Now, if you look at the actual behavior, like downstream impact on the behavior, arrestees' behavior, we can look at the FDA, NCA, and VCA, and then we find essentially the similar results. Like on average, PSA provision doesn't have an impact on on the arrestee's behavior, nor the decision by the judge. Okay, so you could say, oh, that's too bad. Can't write any paper about this. But like if you think about it, this analysis doesn't actually answer the question we are interested in. Okay, in particular, we want to know, like, does PSA provision help judges make better decisions? And this analysis doesn't tell you that, because it only basically asks the question of, does PSA provision influence judge decision on average? So we don't know whether a judge may be going against the decision recommendation in some cases in different directions, and so they may be canceling out. So on average, it looks like maybe there's no impact at all, right? So we need to look further into the data to see if there's more we can learn from. And in fact, if you actually look at the data, you see the judge agree on majority of cases. So this is AI versus the human, which means that this case, like, the judge is not actually looking at the recommendation. So even though they're not looking at the recommendation, you see that the majority of cases they agree. However, like 30% of cases, there are disagreements. In fact, AI seems to be a little harsher. So 20% of the case where the AI recommends cash bail, that judge is sort of releasing the arrestee without any bail. Okay, and there's also the disagreement in the other direction, about 10% of the case. With the recommendation, there's more agreement. So you can see there's more agreement compared to these cases. But again, there's sufficient number of disagreement between the human and AI recommendation. So this, I can make this table because AI recommendation can be calculated for all the cases. Okay, so to investigate this a little bit more, we're going to look at the experimental design. So first, we're going to randomize, as I said, human versus human AI. And one important assumption we're going to make, which is actually guaranteed by the design, is that AI recommendations affect the outcome only through the human decision. So this is guaranteed because the arrestees don't know whether the judge actually received the AI recommendation. So that means that arrestees' behavior is only affected by AI recommendations through human decision, the judge's decision. Okay, there might be confounders between the decision and the outcome, because who knows how the judge is making a decision. Okay. And we have a lot of things that we don't observe, but the judge has the information judge has. All right. So I think this kind of design is widely applicable even when the stakes are high, as long as you can sort of provide randomize the provision of the algorithm. Okay. So let's sort of formalize this a little bit. So I'm going to use ZI to denote the AI recommendation provision. Human decision is going to be denoted by DI, and the observed outcome is denoted by YI. Okay, and the potential decisions and outcome. This is a potential outcome notation. Decision might be affected by the provision of the AI recommendation, and then outcome is affected by both potentially recommendation and a decision. Okay. However, we're going to make this single blinded treatment assignment, which means that if the decision is the same, then the potential outcome does not depend on AI recommendation provision. So we can write the potential outcome as just a function of the decision and not worry about the AI provision. Okay, so the AI recommendation provision only affects the outcomes through the decision. We have a randomization, so the ZI is independent of everything. AI represents the recommendation by the algorithm. So AI is binary, cash bail or not. We're gonna use that to denote AI recommendation. Okay, so these assumptions can be guaranteed by the experimental design. Okay, so that's really important. This is not a statistical assumption. This is assumptions guaranteed by the experimental design. We can use a stratified randomization if you want it. Okay, I want to emphasize there's no other assumption for this paper are required. Okay, the only assumptions we need is these two assumptions that we can guarantee by the experimental design. All right, so to measure performance, we're going to use a classification metric. So it's a 2x2 decision versus outcome. In particular, we're going to look at the y of 0. So this is the behavior the RST would engage if they are released. Okay, so under the condition, under the hypothetical scenario that RST are released, what would they do? Okay, so that's actually what the risk score is supposed to predict. So this is the sort of important outcome to look at. Okay, so the decision is I'm going to call the positive decision d equal 1 as cash bail decision, negative as signature bond. Okay, it's not a normative positive negative, it's just a binary classification. And then the outcome is, for example, NCA. If I'm going to say y of 0 equal 1 if arrestee would engage in new criminal activity when they're released, and 0 if it's no NCA. Same thing for FTA and NBCA. Okay. So what does this mean? Like false positive in this case means unnecessary cash bail. So you made a decision d equal 1, the cash bail decision, but the y of 0 is actually 0. So you could have released that person and that person wouldn't have committed a crime, but you instead gave a cash bail decision. False negative is the opposite. So you gave a signature bond decision and that was followed by NCA, some new criminal activity, negative conduct. Okay, so we have sort of two mistakes that you can make according to this classification table. You can also consider y of 1, but jointly doing so requires additional assumption. There's another paper about this. Okay, so once we have this table, we can basically assign the loss or negative utility to each of these outcomes. And I'm going to set this false negative loss to be 1 to just normalize. Everything is relative to the cost of false negative. Okay. And then we can define something called classification risk. So basically the idea is that you can multiply the loss by the false negative proportion and then multiply by loss for the false positive by the false positive proportion. And that gives you the classification risk.
Sorry, could I ask a question? You said the cash bail was unnecessary, but it's plausible to me that if someone gets cash bail, they would not want to commit a new crime because they risk the bail amount, right?
Yeah, so that's a very good. Yeah, that's a very important point. So I'm ignoring y of 1. So I'm ignoring the behavior that arrestee may engage under the cash bail. So the scenario you described is certainly possible, and you may want to make a different decision based on not just the y of 0, but the joint outcome of y of 0 and y of 1. Like you may want to issue a cash bail only if the cash bail actually prevent someone from committing a crime, for example. But as you can imagine, like the analyzing the joint potential outcome, it requires more assumptions. So for this paper, we're going to be focusing on the y of 0 law. Okay, so other classification ability measures are possible, but I'm not going to talk about it. Other than misclassification rate, which is just the sum of the false negative proportion and false positive proportion, when this loss is equally weighted loss. Okay. Okay. So how do we compare human decisions with and without AI? Basically, we can write the confusion matrix that I showed you earlier in terms of this sort of joint probability of y of 0 and decision under provision or without provision and algorithmic recommendation. And in here, you can sort of see like blue and black. So the blue are the ones that are not identifiable from the data. And you see that all the blues are 1 in the middle. So what is 1 in the middle? That's when the decision is actually cash bail. Okay, so if the decision is cash bail, we don't observe what would have happened if the signature bound was actually a decision, right? So that's why it's unidentifiable. So this is called the selective labels problem in the literature. We don't observe y of 0 when d equal 1. And as a result, these blue probabilities are not identifiable. So basically, half of the confusion matrix is not identifiable. Okay. However, it turns out the difference between these unidentifiable probabilities is actually identifiable. Okay. So here you see that because the z is randomized, y of 0 distribution is the same whether z equal 1 or 0. And it turns out you can write this as a sum of two probabilities. One is unidentifiable, the other one is identifiable. But because these are two are the same, the difference between these two is actually a difference of the two identifiable probabilities. Okay. So what this means is that actually the risk difference can be identified by looking at these differences is equal to the fact that these two difference of these two probabilities is the same as the difference of the observed probabilities. Okay. We can do hypothesis test, but given the time, I'm gonna sort of skip this. And finally, I think we can also compare AI decisions with human alone versus human plus AI. So even though we don't have an experimental arm that just have AI decide everything, we can actually compare these differences. So the reason why you can do that is now the confusion matrix is completely unidentifiable, but you can use the bounds. And it turns out in this case, the risk difference, it can be bounded using just an elementary fact that the unknown probability is between 0 and 1. And it turns out that these bounds are pretty informative, as I will show you in the empirically. You can also come up with a sharper bounds, but it's a bit more complex form. Okay. So now that I've sort of finished explaining the methodology, let me just show you a bunch of results. Okay. So first results shows that the AI recommendations actually don't improve human decisions. So in this figure, on the x-axis, you see different groups. And the y-axis is the impact of AI, again, the probability scale. Positive number means AI helps, and then the negative number means the AI actually harms. Recommendation makes things worse. I'm looking at the misclassification rate, which is the sum of the false negative proportion and false positive proportion. And this is for the failure to appear outcome. And as you can see across the board, it's pretty precisely estimated. Impact of AI is essentially 0 for both false positives and false negatives across different groups. Okay. Same results for NCA. Essentially is very, even if it's not exactly 0, it's pretty small. So the AI is not really helping human make a better decision. And similarly for NBCA, for this even very precisely 0 in terms of how the AI recommendation increases or decreases false negative, false positive proportion or its sum. Okay. The second results that we have is that AI alone decisions perform actually worse than human decisions. So here it's the same figure, but what I'm plotting is not identifiable because I'm looking at the AI alone. So you see that thicker bar, that's a bounds, the estimated bounds, and then confidence interval, 95% confidence interval. Comparing AI alone versus human alone. A positive number means AI is worse, and negative number means AI better. Again, it's a probability scale. So you can see that for FDA, the AI is making greater misclassification rate compared to the human judge decision. And you see in particular, the false positive proportion is basically driving this result. So AI is unnecessarily being harsh compared to the human judge decision. Okay? You see the similar pattern for comparison against the human plus AI. again, the false positive proportion, the AI alone decision has much greater probability. You see the similar pattern for NCA. Again, the false positive proportion is much greater for AI alone recommendation than the human decision or human plus AI. So if you sort of let the AI make a decision in itself, then what you will see is that you will see a lot of unnecessary cash bail decisions in this case. Okay, and same thing for NVCA. Actually, here the problem is even worse. The almost 15%, about the 15% percentage point greater proportion of false positive recommendation by AI. Okay. All right. Now, I didn't quite explain clearly, but you can do a hypothesis test and then invert the hypothesis to decide, because whether you prefer more lenient decision versus more stricter decision depends on your loss function, right? Your preference. So if you remember that the little parameter L is the relative preference of false negatives versus false positives. So depending on which one you care more about, you may even prefer AI sometimes. Okay. So in this graph, you see that on the y-axis, you see the loss of false positive and loss of false negative. So relative importance, which one do you care more? So the greater than 1 means that you care about false positive more. So like you care about making a mistake, like you assign a greater loss to the false positive decision, which is the cash bail decision, even though signature bond decision would have led to no new crime. Okay, and less than 1 means the opposite. You care more about false negatives, that is issuing the signature bond decision and resulting in a negative outcome. So you can see overall non-white, female and male. Green means human alone, human decision is preferred. Red means AI alone preferred. In this case, no matter what the loss function is, at least in this range, you basically prefer human alone decision as long as the cost of false positive is high. Dotted line means that statistically indistinguishable. Okay. Similar results for NCA, except maybe you may prefer AI alone for non-white arrestees if you care more about the false negatives than the false positive. Same thing for NVCA. So in most cases, in this particular application, we care about we prefer human alone system over the AI alone system, so long as you care more about the false positive. This makes sense because it's the human judge in this case is more lenient. Okay. Final results is the racial disparity. So in this graph, I'm plotting the racial disparity for 3 different decision-making systems: AI, human plus AI. And positive number means that there's a greater error for non-white arrestees, and negative number means that there is a greater error for the white arrestees. Okay, all 3 decision making seems similar across for the misclassification rate and also false negative proportion, but false positive proportion, maybe AI is sort of biased against non-whites, right? So they tend to make more false positive decisions for the non-white arrestees than the white arrestees. That doesn't seem to be the case for the human plus AI. Similar results for NCA, although in this case confidence interval is overlapping, and perhaps maybe the human AI plus AI is being more lenient for non-whites there. for the similar pattern arises for NVCA. Again, AI seems to be a bit more harsher for non-whites compared to the white arrestees. Okay, so to just wrap up, so we propose a methodological framework for experimentally evaluating these 3 different decision-making systems. The proposed methodological framework is actually widely applicable. I talked about single blindness treatment assignment, and it doesn't require the AI alone treatment condition. Okay. I think what's nice about this framework is that no additional assumption is required, but the bounds are pretty informative. We have open source our software package called AI Human. So if you have this kind of experiment, you can analyze that data using this package. We conducted and analyzed the RCT that evaluates the pretrial risk assessment instrument. And then we find basically that the AI recommendations have little impact on human decisions, and AI decisions tend to perform worse than the human decision. So I'll stop here. Yeah, and if you have any questions.
That's excellent. Thank you very much. Does anybody have any questions? Feel free to raise your hand. We'll start with Michael.
Yeah, so I have a couple of questions, substantive ones here. So the first is whether you've looked into any other information about the cases to see why you're getting those false positives. Like, are there court records that show, you know, somebody got vouched for by you know, a teacher or something, and that and the AI doesn't see that, and that makes a difference. And the other question is, do you have data on the amount of experience judges have? And have you thought about comparing experienced judges who probably just ignore what you hand them versus somebody first day on the bench might take that more seriously?
Yeah, those are great questions. So we are in the process trying to get more information, like affidavit or court transcripts, because the judge may engage in a conversation with arrestee. Judge may learn a lot about arrestee themselves. Yeah, so I think a lot of this, like, basically in this case, the judge has more information, and that might explain why the algorithm doesn't perform well. Yeah, experience is another one. That's basically part of the information that the algorithm doesn't have, because algorithm is trained on the nationally sort of collected data sets, not a locally, collected data. So the algorithm is not fine-tuned to the local environment. And I think that may explain why the algorithms tend to be harsher. Yeah, so in this experiment, there's only one judge. So don't Google. But we have other experiments across different jurisdictions. So we don't have enough to really characterize how different judges take these recommendations differently, but we have some variation there in the future papers we'll be writing. But we can also learn. One thing we are looking at is like learning over time. So even a single judge may learn, people get rearrested, come back. So the second time, the judge may treat the AI recommendation differently depending on how the first decision went wrong or correct. So there's a lot to look at in this data set, how the human recommendation interacts over time, and other interesting questions.
Douglas?
Great, thanks. I just wanted to ask a question. Maybe I'm not sure if you care to speculate on this. The non-white bias, do you think that was perhaps reflecting a bias inherent in the training data, which is reflecting systemic differences in policing? Do you think that's possible or probable?
Yeah, that's a very good question. So if you think about what inputs go into the algorithm, it's essentially the criminal history alone. The race itself is not used, but obviously it will be correlated. And this study is also conditional on the arrests. So there's bias that may come into the arrest at the arrest stage. Yeah, so it's a sort of difficult question about like if you want to create an algorithm that's sort of fair in terms of like reducing the racial disparity, you do need to have a race information in there to construct the algorithm. But at the same time, that's probably not constitutional. So, there is this dilemma of, okay, like how we, use how we use the race information, whether we can or we cannot. But it's all, coming through this criminal history. So all the systemic information, the biases that exist in society is propagated through this criminal history inputs. And it's hard to know what to do about that.
Yeah, thanks. Yeah, it may be insoluble, but it's probably crucial to acknowledge it up front and make sure that people understand that when they're looking
That's
at
right.
decision making. Thank you.
Yeah, no, that's a very good point. Yes.
Michael?
Yeah, hi. Thank you very much for the talk. So I had two questions, if it's okay. I'll ask both of them. So one is, I wonder to what extent those statistical tests are influenced by just measurement error, right? Because you have uncertainty about whether someone who might have committed a crime was actually caught. And you also have uncertainty about whether someone who was arrested was actually at fault. So those could go both ways. And it seems like with small effects, those might just overwhelm the estimate, right? Or maybe not.
No, that's a good point. So so it's arrest, right? So it's the outcome is arrest. So it's different from the conviction.
I mean, that way, and also probably most people who commit, petty crimes are not actually arrested.
Right. So I think the results, I mean, it's not a measurement error in the sense that if you are arrested, it will be in a database. But it's a measurement error in the sense that maybe arrest is not what we care about. If we care about the actual conviction or some other outcome.
Well, I mean, I would care about whether it actually happened or not.
Oh, okay. Happened meaning that actually whether the person
actually did it. Yeah, so that is what I refer to as the measurement error, right?
Yeah, no, that's fair. I mean, I guess that would require sort of, merging this data set with the police records and getting, more in detail. But yeah, no,
I would say that maybe ideally this should go into the estimate of the p-value, right?
But I don't know how to account for that if I don't know, the extent to which, some of these cases or some of the cases are being missed or, So
I mean, it's not a small proportion, right? It's probably a huge proportion, actually.
That I don't know. That's a good question. Yeah. That I don't know. Yeah.
So if I could quickly ask the other question. So as I think most people know, but I'd like kind of to have your take on that as well. So of course, you'd have disparities in false positive rates, even if the system is perfectly calibrated, if the base rates in the populations are different, right? So to what and I'm sure you're familiar with Sharad Goel's takes on that. What is kind of your take on that control
I mean, in this case, I take his critique as to like it depends on what you condition on, right? Like it's I don't see it necessarily as a problem. It's just like a different quantitative interest. Here, racial disparity, I mean, we're really looking at, among the cases of the non-white arrestees versus white arrestees, that how many, cases where the person wouldn't have committed a crime if they're released, how many of them are actually receiving a cash bail decision? And that proportion is basically being compared. So I'm not sure what the potential, critique other than the fact that people might be interested in some other quantity.
Yeah. Thank you. And thank you for releasing the data set as well. I'm looking forward to
Oh,
that.
yeah.
Thank you.
Yeah, we'll continue to release the data as we conduct more study. Well, there's a second half of this data set, and also there are other jurisdictions that we are currently running the field experiments. So.
That's great. Thank you very much.
Linda?
Hello. Hi. Can you hear me?
Yeah.
Just making sure it works. Okay, great. Thanks for the presentation. I felt that the design portion of it, like the idea of how to do the experiment, was quite interesting. But the question I have, and it's also partially a comment, is related to that aspect, in particular the central question you're asking, right? Which is whether an AI can help humans make better decisions, right? But doesn't that depend, in a sense, on the quality and accuracy of the AI itself, right? So I was curious as to like whether like, because the examples you gave, right, for these different AI systems, at least in pretrial assessment, were actually less effective than the judges, or less good, quote unquote, right, than humans. So I was just wondering, like, because it'd be really interesting to do this on a study with an AI that actually made better decisions than humans. But I don't know if you know of any that are there. Yeah.
Yeah, I think in the medicine, I think there are a lot of instances where the AI is outperforming the human capabilities.
Exactly.
So maybe in those instances, criminal justice system, I think it's it's a difficult one. To be fair, it's difficult to predict this behavior, and the information that's being used to predict is just so sparse that it's no surprising that it doesn't perform well. One thing we are looking at is you can actually try to figure out like when the human should ignore or when humans should follow the AI. So if you remember, there's like about 30% of the cases where they disagree, and it would be interesting to see when they should override and when in what direction. So some of that you could learn from the data. And you can, and also some of that you could try to come up with a better algorithm by trying to, use this data to see if you can change in a way that actually more helpful. So yeah, so there's, I think, a lot of interesting questions we can ask here.
That's why it's really good that, again, like you've released this package for other people to use, because I think applying it to different types of AI would get interesting results. Thank you.
And the other thing I think would be interesting is like currently, like in this experiment, there's an information gap between AI and judge. A judge has way more information. So it'd be interesting to see like what would happen if you actually feed the same amount of information. Can we then actually come up with a better better algorithm?
Madison?
Hi, sorry, I'll go off mute, everyone. Hi, thanks for the presentation. I think my question builds on Linda's a little bit about the case and the application of this model. So I'm curious about, I think a lot about how government is using AI and data. And so when reading through this framework of your presentation, thinking about, is this model, could it be used as like a risk assessment for government, for example, to identify whether they can or should not implement an AI tool? So it's, I guess my question is, are there other cases where you think that this model, it could be well suited to outside of the criminal justice landscape? And maybe a bit similar to Linda as well, like, are there, outside of the medical context, where are there areas where we are seeing AI actually assist in the decision-making? And in that case, this model would be good at showing us that. But yeah, I guess the future of this model, where does it go?
Yeah, I mean, there's a lot of, not necessarily government per se, but like renting decisions, housing, subsidies, that type of decisions, like who should be, given the mortgage or, other credit card agencies. So there's a lot of sort of decisions that the algorithm is currently being used to evaluate the applicant, and then the humans are making the final decision. So that's sort of the settings where something like this could be methodological framework could be used. And the other thing I wanted to mention is that here AI alone system, you can basically like use any kind of AI alone. So I actually we're thinking about doing like feed the same information to ChatGPT and then ask whether this person should be given a cash bail or being released, and then you can use that data to with this experiment and then evaluate. There's nothing like an AI alone arm. There's nothing about that to be actually real, because you don't need to use any experiment. So you could evaluate different alternative decision-making system, and then see how that how that goes once you are able to conduct some kind of experiment like this.
Thank you.
Are there any other questions from folks? Maybe if I can just briefly ask one at the end. And it's more of like, how do you approach your work? Because you have all these different interests, and all these variety of areas that you're publishing, and like, how do you manage all of this, all this variety, right? Do you have Mondays you do X and Tuesdays you do Y?
I see. Like I do parallel processing. So not literally parallel, but I'm working several projects all at the same time. Yeah, I mean, it's obviously like a few hours here and there. I work on a different project, but I find it useful to sort of pursue multiple projects at the same time. There's sort of the cross-fertilization. Sometimes the ideas from one project can feed into another. The other thing is like once sometimes you get stuck in one project and can't make a progress, and then shift to another. And yeah, so it's sort of that's how I try to deal with it. But I'm struggling too. So.
Well, I guess we'll just say thank you very much for a wonderful presentation.
Yeah, thanks for having me. I
Really appreciate your time.
Yeah. All right,
thanks for joining,
guys.
everyone. Have a nice weekend.
Thanks a lot.
Bye.
Bye.